Awesome. So, hi everyone. Thank you so much for joining today's seminar of the TC on model-based optimization for robotics. I just want to make very brief, quick announcement. So, this is actually the first seminar series of this, first seminar of this series of 25 to 26. So, we will have a couple of, I believe this is the last one for this year, but then we have already a couple more lined up for next year. And you can find the current schedule on our website at this link here. And then I just wanted to quickly announce that we also started the nominations for the yearly Best Paper Award of the TC. So if you had an awesome paper published anytime in the year 25, then, and it has to do with basically optimization and robotics, then you would definitely be eligible to nominate your paper for this Best Paper Award. Applications will be open until early February, and we will be announcing the winners in around April, and it comes with a nice travel award for any robotics conference in the coming year. So make sure to remember to nominate your papers. And then with that being said, maybe Heng, if you could start sharing your screen, and then I will do the quick introduction.
Okay, let me see.
Thank you.
Good.
Okay,
Can
awesome.
you see it? Okay.
Yeah. So it's our pleasure to have Heng Yang give a talk today for us. So Hank is an assistant professor at Harvard University, where he leads the computational robotics group. And I've known Heng Yang's work for quite a while now. During his PhD, he helped popularize SOS and moment hierarchy methods to do certifiably optimal robust estimation, amongst other things, which was really exciting and very impactful work. And since then, he has, with his new group at Harvard, he has continued this work, but also delved into very new, cool control problems. And I'm excited to hear what you're going to talk to us about today. So
Okay.
Thanks a lot, and the stage is yours.
Yeah, okay. Thank you guys. Thank you for attending my talk, despite that it's been very close to Christmas. It's okay. So today I want to talk about my group's recent work about, continuing the semi-definite relaxations, for robotics problems. But in the end of the talk, I also want to highlight a bit of the recent theory work that we've been doing about understanding the dynamics of these first order SDP solvers. And I think that's, something that gets me very excited these days. And I hope that I can spend maybe 5 to 10 minutes telling you about some of the things that we found. Okay, so the structure of today's talk is I'll first spend maybe 10 minutes, 15 minutes talking about moment ensemble squares relaxations. So that will basically give us on the same get us on the same page about what this tool is and also its challenges, to maybe mostly in terms of scalability in applying to some of the problems that we care about. And then the second part of the talk, which is maybe the most important part of the talk, is I want to talk about how we can leverage structures in robotics problems to scale up these moment SOS relaxations. Specifically, I'll talk about two things. One is XM, which is for a perception problem, and then the other one is Spot, which is for motion planning and control. And as I said, in the end, I want to spend some time telling you about the exciting new findings that we have been working on about SDP solvers. Okay, so with that, I'm going to get started on this, the background. So I want to first start with like the quadratic constraint quadratic program. Like here we have on this slide we have QCQP. So in this QCQP, our variable to optimize is this little vector x, and it's an n-dimensional vector. And then our objective is convex, is a quadratic function, not necessarily convex in x, and our constraints are also quadratic constraints in little x. So the problem data here is the vector B, the matrix C, and also the constraint matrix C is A1 up to AN. Right, so this problem you can easily identify it as NP-hard in the worst case because you can model binary variables, combinatorial problems using these constraints. Okay, so the problem here is, we're facing a non-convex problem, and in general, if we apply gradient-based methods, there's this chance that it might get stuck in local minimum. So the goal here is, can we use, convex relaxation techniques to get, very good near optimal solutions to this non-convex problem. So I want to first introduce this short semidefinite relaxation, which is easy to understand, and then I will generalize it to the moment SOS. Okay, so in short relaxation, we do 3 steps. So the first thing I'm going to do is I'm going to create a matrix variable, big X here. It's going to be the little x times little x transpose. So by construction, this will be a symmetric matrix of size n by n, right? And then because this matrix variable now is quadratic in my original variable little x, and my original problem is a QCQP, right? So everything was quadratic. So now you can easily identify that now the objective function becomes linear in big X, right? And then also the constraints also become linear in big X. So they were originally quadratic, but now you lifted the variables to quadratic. Now everything becomes linear. Okay. So the last thing I want to do is I want to observe that this big matrix X is not just an arbitrary symmetric matrix. It needs to obey certain constraints. So the 2 obvious constraints, and actually the only 2 constraints that it needs to obey is first, it needs to be positive semidefinite, right? Because big X is the outer product of a vector little x. So by construction, this should be positive semidefinite. And then the next one is that the rank of this matrix X has to be equal to 1. Okay. So, and then because I said, and you can also convince yourself that if big X is positive semidefinite and also rank equal to 1, then it must admit a rank 1 outer product like that, like the one I started with. So therefore, these 2 problems are actually equivalent to each other, right? So on the left, I have my original QCQP, which was non-convex. And on the right-hand side, I have a rank constrained semi-definite program, right, with the rank of X equal to 1. So because these two programs are equivalent to each other, so it must be the case that the rank constraint SDP is also non-convex, right? So in general, I don't know how to solve this rank constraint SDP as well. Okay, but then in the rank constraint SDP, the nice thing is that the only non-convexity that's left is this rank constraint. Therefore, I can apply a simple convex relaxation and just drop this rank constraint. Okay, so after you drop this rank constraint, you are trying to minimize, a function over this space, and you have dropped the constraint, which means that the space have grown larger, right? So because the space has grown larger, you have this very nice lower bound in the sense that the optimal solution of the SDP, now removing the rank constraint, must be a lower bound of the original P star. And then, on the other hand, if you can apply some local solvers to the original QCQP, you'll get a p hat, right? And then this p hat is going to be perhaps a local minimum, and then it will be an upper bound to the true global minimum p star. So therefore, by doing so, I've dropped the rank constraint on the right hand side. Now I get a convex SDP. So I get this relative subauthentic gap, right? Which is I get this sandwich, which I have a lower bound f star and an upper bound p hat. And by comparing how close is this lower bound to this upper bound, I can evaluate the quality of this of the local minima p hat. Okay, so this is what we call an optimality certificate, right? So basically, when this eta is very close to 0, or maybe 10 to the negative 3, 10 to the negative 4, then I'm very confident that I've found a very good optimal solution, near optimal solution to this problem. Okay. So let's just recap what we did, right? So to solve this non-convex QCQP using a convex SDP, I first use this lifting to create a matrix variable, and then everything becomes linear because the original problem was QCQP. And then I did a strengthening, which is I observed that this big matrix X has to satisfy certain conic constraints. Okay, and then I dropped the rank constraint. That's a simple SDP relaxation. Okay, so this SDP relaxation, as I will show you later, is already very powerful in lots of the robotics problems. But in later, when we study some of the control problems, this SDP relaxation turns out to be not sufficient. And because of 2 reasons. The first reason is that if you apply these short relaxation to some very hard non-convex problems, you tend to get very large subauthentic gap, right? So basically this eta can be arbitrarily bad, right? So maybe it's very close to being equal to 1. In the sense that you get a mostly vacuous lower bound to this global optimal value P star. And the other thing is, it's not very natural to handle high order polynomials in some of the control problems that we will see later. Okay, so what is the fix, right? Is there a way that we can generalize this, simple to understand short SDP relaxation to, more like a larger family of problems? So at this, at the turn of this century, there, Lassier and Perillo, they published kind of a couple of papers. One, it was on, a global accommodation with polynomials and the problem of moments. So this, and then the other one is, from this, from the sum of squares type of perspective. So this two papers, they basically, one was, more in real analysis, and then the other one, it was more on algebraic geometry, right? So these two things, they converge together into this beautiful field of moment and sum of squares, which I'll tell you a bit about it. Right. So my presentation in the next slide will not be very mathematically rigorous, but I want to show you a more application-driven perspective of this of this machinery. Okay, so we started with the QCQP. Now we're going to generalize the problem class to a general polynomial accommodation problem, in the sense that my problem data now are polynomials, right? So here P, H, and G, they are polynomials of degree up to 2 times D. So you can when D is equal to 1, then this recovers my original QCQP. Right? So my optimization variable is still this little vector X, which is n-dimensional vector. Okay, this is, this because it subsumes QCQP, it must be the case that this problem is still NP-hard in general. Okay, so now I'm going to, generalize the previous semi-definite relaxation, 3 steps of it, in this, using this moment SOS hierarchy. So the first thing I'm going to do is I'm going to do this lifting step to create a matrix variable. But I'm going to create a much larger matrix variable. Right? So the way I'm going to do this is first I'm going to define this vector v, which is indexed by a subscript kappa. So this bracket x subscript kappa, with kappa being an integer, that's at least as large as d, is a vector of monomials in x of degree up to kappa. So let me give you just one example. Right? So if my original little x is 2-dimensional, and then V2 here will contain all the monomials in X of degree up to 2. And then in this simple case, I would get this 6-dimensional vector, which is 1, which is a 0-dimensional monomial. And then X1, X2, which is the order 1 monomial, right? And then I have the second order terms, X1 squared, X1 times X2, and also X2 squared. Okay, so I created this longer vector V of 2, right, which actually contains little x plus its 0 order and high order terms. Now I can create this similarly, this matrix variable big X, and I also am going to index it by this integer variable kappa. So it's going to be the outer product of V of kappa, right? So it's going to be V kappa times V kappa transpose. Again, in this simple case of 2-dimensional X and 2-dimensional relaxation, I'll get this matrix variable X, which you can observe contains all the monomials in little x of degree up to 4 now, because the original vector has degrees up to 2. Now, this outer product will have degree up to 4. Okay, so I'm going to call this moment matrix, although that's not exactly the definition of a moment matrix, but I'll give it a name here. Let's call it the moment matrix. Okay, so now you can observe that because by design this V of kappa contains the monomials in X of degree up to kappa, and X of kappa is the outer product. Therefore, it will contain the monomials in X of degree 2 times kappa. And 2 times kappa is greater or equal to 2 times d, which is all the degrees in my original polynomial. Therefore, you get this linearity, property again, right? Because the objective before it was a polynomial of degree up to 2d in x, in little x. Now, because I have this x of kappa, which is has this many high degree monomials in it, it's going to be a linear function of x of kappa. Similarly, for the constraints, linear constraints, let's say, it'll contain equality constraints. It'll be linear in my x of kappa as well, right? So this linearity still holds. And lastly, I'm going to do a similar thing, which is I'm going to observe that this moment matrix or this x of kappa is not going to be any arbitrary symmetric matrix, but it has to satisfy certain structural constraints. The first thing that still holds from this x of kappa to be positive semi-definite, and also the rank of it also needs to be equal to 1. However, there is much more. There are many more constraints that this x of kappa needs to be satisfied. For example, I'm just going to tell you one of this kind of examples is if your original monomial x of I of x is equal to 0 for any x that's feasible, then this xi of x times any monomial x to the power of alpha also needs to be 0, right? Because 0 times anything is 0. But as long as x of alpha, is such that the total degree of hi times x of alpha is still bounded by 2 times kappa, then I can write these kind of constraints also as linear constraints in my moment matrix. That's just one such type of constraints. You can also add other constraints, which for the sake of time, I'm not going to talk about the details. But at the end of the day, what I'm trying to say is that there is a very principled procedure. You can actually automate this procedure. You can automate in code that can enumerate over all these possible constraints that can be added to the moment constraint. And together, they define a cone, actually a convex cone, that's called the moment cone, right? So that's the basic idea here. Okay, so now by generalizing the original short relaxation to the polynomial case, I can get this multi-block semi-definite program. Everything here remains the same in the sense that I have a block of many positive semi-definite variables, which I'm trying to optimize a linear objective over it, and then it needs to satisfy a bunch of linear constraints and also this rank constraint. Similarly, I'm going to drop this rank constraint because after dropping the rank constraint, everything becomes convex, and ideally, I can solve this convex program. So after this dropping rank constraint, you get similarly this lower bound or this sandwich type of property in the sense that f of star for any relaxation order, so kappa here, I'm going to call it relaxation order. For any relaxation order kappa is going to generate a valid lower bound for the original non-convex objective p star. And then if you can manage to solve the original polynomial optimization problem using some local solver, then you get an upper bound p hat. And then I can similarly generate this relative subarithmetic gap. That's the difference between the upper and the lower bound, right? And then what's nice about this moment SOS hierarchy is that you can guarantee as you increase this kappa, this relaxation order, which means that you're going to increase the vector v, larger, larger, and larger, and also by product you will generate a very large, moment matrix variable. Right? So the story here is essentially if you can solve this, very, very large moment SOS relaxation, then eventually you will converge to the global optimal solution of the polynomial optimization problem. So here, it should be noticed that this does not say that P equals MP, right? Because on the right hand side, I have a polynomial time solvable SDP. On the left hand side, I have something that's MP hard, right? So this tells you, in the worst case, you need exponentially large moment matrix to solve this non-convex problem. So still, the theory is valid. Okay, so this is we are going to call this optimality certificate, right? And then you remember that when I increase this kappa larger and larger, I'm going to get the smaller optimality certificate. Eventually, you get something very close to zero. Okay, so that's all I want to say about a background about moment ensemble squares. So just in summary, so there's this very principled procedure. As a user, you can write down your polynomial optimization problem, as a symbolic program. Let's say, in SymPy or in MATLAB, using some symbolic, definitions. Right? You can write down your polynomial optimization problem. Then there's this procedure, which I'm going to tell you a bit more about later, that can automatically generate a convex semi-definite program. And after you generate this SDP, you can pass it to any convex SDP solver. So, for example, the most robust one would be, the commercial solver MOSEC. And then you can solve this program to get a lower bound f star of subscript kappa. And then potentially from the solution of this SDP, you can do some rounding procedure to generate a near optimal solution, and then using this to locally optimize starting from this initialization. For example, using fmin_conv, right? And then you'll get a p hat. And then I'm going to compute this difference between upper and lower bounds to get an optimality certificate. So that's the story here, right? So as that's application-driven type of perspective of this so-called certifiable optimization. Okay, so let's now, I want to now tell you a bit more about the challenge of applying this, right? In the sense that we're going to do some simple calculations. So let me call little n the dimension of the original polynomial optimization variable x, right? And then I'm going to call big N the size of the largest positive semi-definite variable on the right-hand side of this SDP, and big M the number of linear equality constraints in this multi-block SDP, right? So little n is the size of the original problem, and big N and big M are the size of the convex relaxation. So there are two cases depending on how I do the relaxation. If I do the short relaxation, which is the first order relaxation, then you have the nice property that big N and the big M are roughly the same order of little n. So in the sense that you get the similarly number of constraints, but then the size of the problem becomes a quadratic in the original problem, right? Because you have an n by n matrix, so there's a slight increase in the dimension of the problem. However, there's a worse news in the sense that if you starting to apply high order relaxations, for example, kappa equal to 2 or even higher, then the relaxation becomes very difficult to manage in the sense that big N here, which is the size of the largest positive semidefinite variable, will be size n squared by n squared. So simple calculation tells you if you have an original polynomial optimization problem which has dimension 1,000, then this tells you you're going to get the positive semidefinite variable that's 1,000,000 by 1,000,000 roughly, right? Okay, and the number of constraints, big N, will be roughly n to the power of 4. In the sense that you'll get about 1 billion linear equality constraints, right? So roughly speaking. So that tells you, the sort of the speed of increase in the dimension of the convex relaxation if you go higher and higher order in the relaxation, right? So let's then talk about, what are the capabilities of the off-the-shelf, solvers these days, right? So if you apply like things like MOSAC, which is the most robust solver up to date, they can solve very large problems. But then if you compare with the growth of this, convex relaxation, then they are actually not that much. Because so in order for MOSAC to solve a certain problem, I mean that solvable in terms of hours, not in terms of real time, you need N to be typically below 5,000 by 5,000, and big M, less than 500,000. So it's considered very large scale problems, but they're just too small compared to convex relaxations, especially this moment SOS relaxations. So, and I'll show you later that unfortunately, if you want to apply some of this technique to the robotics problems, in many cases, we're going to generate very large problems that are out of this comfort zone, right? Okay, so then comes to the a major part of this talk is how are we gonna, we're not going to be, there's this big hammer here that can solve any, polynomial optimization problem. We're going to try to apply it, right? But then when you apply it, you better leverage some structures. Otherwise, there's no hope this thing can scale. Okay, so in the first case, I'm going to talk about the application of it in the perception problem, which is this bundle adjustment problem. Okay, so let me spend maybe 5 to 10 minutes on this. So let's first talk about what is this structure from motion problem and also the bundle adjustment problem. So the problem here is you have a sequence of moving cameras, or maybe different cameras in the 3D space, and then all these cameras they co-observe the 3D structure that you're interested in. And then you get maybe n images, right? And then the goal is to reconstruct the 3D environment. So this structure from motion or bundle adjustment problem has been a cornerstone result in computer vision. For example, the famous paper Building Rome in a Day, basically they collected millions of images from Flickr back then, maybe 10 years or 15 years ago, and then they were able to reconstruct major buildings in Europe just using this structure from motion type of pipeline. So how does structure from motion works, or 3D reconstruction works? So typically you can decouple the structure from motion in terms of 2 stages. So the first stage is you're going to do some feature matching, looking for similar points across these images, and then you're going to create what we call a view graph. So this view graph is very simple, right? So this view graph, on the view graph, you have 2 types of nodes. One type of node are 3D poses, right? Or basically the camera poses. And then there's another type of nodes, which are the points in 3D, right? So basically, these are the variables you want to optimize, right? Because I don't know the poses of the camera and I don't know the 3D structure. Okay, what you do have are measurements, and these measurements will become edges in this graph, right? So let's say if in the first image I observe the first point, then you're going to get a pixel level measurement of this point on that image, right? Of course, these measurements are going to be noisy, and then so on and so forth, right? You can generate lots of measurements, between points and poses, right? So the problem after this view graph creation becomes, can I estimate values of the variables on the nodes, using measurements on the edges, right? So that's the problem, in my opinion, very clear formulation of this bundle adjustment problem. So then, to do so, we're going to use nonlinear least squares, right? So my optimization variables are going to become the point and the poses, right? And then I have measurements uij. And in the ideal case, if all these measurements are noise-free, then each uij should be the reprojection of the 3D point first transformed into the camera's frame and then getting projected onto the camera. Right? So this is what people call the reprojection error. So basically, you have the 3D space. You're going to rotate it using the using the pose, and then you're going to reproject onto the image plane. And then I'm going to calculate the distance between the reprojection error. Okay, and then the reprojection here is something that's difficult to optimize, is because you have a 3D point. Now you reproject into 2D. You're going to divide the xy coordinate by the depth v3. Right? So that gives us a nonlinear least squares problem as written here. So there are lots of solvers designed to solve these type of problems, and they work very well when you tune the parameters very well. So for example, COMAP is for the method of choice, and there are series and GTSAM other famous solvers here. But then all these solvers, they have two type of disadvantages. The first thing is you typically need to initialize these solvers quite well. If you initialize it badly, then they're going to convert to a local minima. Okay, and the second thing is, typically, for example, for methods like COMAP, they're very slow. They're slow because, they want to maintain robustness by doing incremental 3D construction. Incremental means that they're going to construct 2 images first, and then, build another image to do 3 views and 4 views, 5 views, 10 views, up until 1,000 views. So because they are doing things incrementally, they are very robust. But they are, that also makes them quite slow because, you are doing more computation than you should. Okay, so as an example, in the original Building Rome in a Day paper, the largest component they were able to reconstruct is from 2,000 images, and they had to reconstruct, only the optimization takes 8 hours, right? And the matching takes even longer. So that's the drawback of the existing solvers. Okay, and the key difficulty, as I mentioned, is because you have this ugly, projection operator. Okay, so then, nowadays, we're in the era of foundation models, right? Especially people have trained, very large, monocular depth prediction models. So this enables me to, for example, if I originally only had a 2D key point measurement, I can now zero shot generate its, a pseudo depth of this point, right? So I'm going to lift this measurement from 2D to 3D, and I'm going to call it U tilde. So now all these measurements, because they have pseudo depths, you can lift them into 3D. So the lifting into 3D gives you this advantage that you don't necessarily need to compare the reprojection error, but you can directly compare points in 3D, right? So for example, here, because and the other thing is these monocular depth prediction models, they typically have a scale bias, between each images. So now I'm going to formulate this scaled bundle adjustment problem, which additionally, I'm going to estimate a scaling correction for each measurement. Okay, and then so therefore, if you scale the pseudo depths, right, you get SI times U tilde, and then you rotate that to the global frame, and you compare the distance between the point and also the landmark you're trying to estimate. This gives you the 3D distance. This now gives us, actually a polynomial optimization problem, right? Because everything in here is polynomial, right? So the objective function is, because I removed the projection function, now I get a polynomial, right? And then all my optimization variables, I can write them as polynomial constraints. Okay, but the bad thing here is that as you can observe, you have SI times RI, and then doing a square. So this is actually a degree 4 polynomial, right? So what I'm going to do is I'm going to do a little bit of massage of this problem to make it a quadratically constrained quadratic program. So the first thing I'm going to do is I'm going to solve the translation variables and the 3D landmarks P in closed form, right? Because those things are unconstrained. So when I have variables unconstrained, I can set the gradients, partial gradients with respect to them to 0, and then write them as functions of my the rest of the variables. So when you do so, you get an optimization problem that's only in terms of SI, the scaling factors, and also the rotation matrices R1 up to Rn. Okay, so this is still a degree 4 polynomial, but now a little bit cleaner than before. So now I'm going to do another change of variables, which I'm going to define new variable R bar, which is the S times R. And then because I defined this new variable that's quadratic in my original R and S, now I get a QCQP. Right? So I get this R bar. So now my optimization variables are these R bar. They are what we call the scaled orthogonal group, right? So it's still very similar to the original SO3, but just with fewer constraints. So now I get a very clean quadratic constraint quadratic program. Now we are ready to apply what we have learned from the first slide, which is do Shor's relaxation. The way I'm going to do this is I'm going to create a matrix variable big X, right? So now it's R transpose times R. And then you get this very nice semi-definite program, this very well structured, in the sense that the only constraints of this PSD variable is that the diagonal blocks, they have to be scaled identity matrices. And these are linear constraints that you can enforce for the SDP. Okay, so I get this very nice, SDP, a convex problem. What if I solve it? The first thing I do is I'm going to throw this to my solver MOSAC and see if the relaxation is tight. But I'm going to compare the sandwich, right? I have a lower bound and upper bound, if you still remember. And I'm going to compare the subalternative gap. So if you do this, you get very excited. As I was in my PhD, originally I do this in lots of perception problems. You get, almost zero alternative gap. So that gets you very, very excited because, basically you have shown that you can solve a non-convex problem empirically tight using a semi-definite program. However, for these kind of large-scale bundle adjustment problems, you face a scalability issue in the sense that if you have lots of images and you want to reconstruct large-scale scenes, you'll see that you're going to get the matrix variable that's maybe 10,000 by 10,000, which quickly gets intractable for or too slow for these off-the-shelf solvers MOSAC to solve. Therefore, we borrow a technique from optimization which is called the Buehler-Montero low-rank factorization, and this Buehler-Montero low-rank factorization, what it does is it's going to factorize this positive semi-definite variable as the outer product of a vector itself with itself, right? And then this outer product now, this tall matrix will actually be on a Riemannian manifold, right? So therefore, what you eventually get is the optimization problem that's similar size as the original problem, but now as a Riemannian optimization. But then here, one thing that I want people to stop and think a little bit about this is originally a little bit counterintuitive in the sense that you started with a non-convex optimization problem and you relaxed it into a convex problem. Now what I'm proposing here, or what Buehler and Montero proposed, is I'm going to rewrite this convex problem again as a non-convex problem. That sort of defeats the purpose, right? Because you started with non-convex, you want to get to global optima. Why do you still need to go back to the non-convex optimization camp? So the nice thing about this low rank factorization, or the answer to this puzzle, is that there are still certifiable guarantees you can do through this Riemannian staircase. What you do is you can start with a rank 3 factorization of this matrix at big X, and you can solve it, right? And then you can check if the optimization is tight. If it's not tight, then you can add one more column to this tall matrix, and then you are guaranteed to escape this saddle point. And then you can keep doing this, right? And in the worst case, you may need to increase your rank arbitrarily large, which defeats the purpose of scalability. But however, in practice, right, empirically, we observe that starting with R equal to 3 or R equal to 4 is sufficient for this method to converge. So eventually, what you get is a Riemannian optimization problem that's similarly scalable as the original problem, but you get the benefit of getting the optimality certificate. Okay, and the last thing we do is that we still think these MANOPT or these MATLAB implementations are too slow, and we want to put these things on modern hardware. So we implement everything in CUDA, right, to leverage parallelization in this Riemannian optimization. Okay, so then the question is what's the math worth it, right? If I've done so many things, do we get a better solver out of this? Okay, so we're going to do here I'm going to walk you through some results that we get, right? So the first result is this original building Rome in a day data set. So here, let me parse a little bit the table here. So here on the across the columns, I have 4 different data sets with increasing sizes, right? So for example, for BAL 1934, what it means that you have 1934 images, and then you want to reconstruct from this many views. And then there are that many landmarks, in that problem. So the largest one is about 10,000 images here. Okay, so we're going to compare. Here there are different solvers here. So the series solver is a classical bundle adjustment solver without learned depths, right? So it's going to do the nonlinear least squares in its original form. So you can see that this method only works when you provided good initializations, and this as expected, right? So if you initialize very well, they are very fast and they works very well. And then this manopt is our algorithm, this SDP relaxation, doing Buehler-Monteiro Lorentz factorization, but it's implemented in CPUs, right? Okay. So you can see that, you get, it's initialization free, but then the solver time is quite slow, right? So it's, you can solve the problem to global optimality, but it's quite slow. And XM here is our solver implemented in GPUs, right? And you can see that it's very fast, right? Compared to manopt, right? And then it's also initialization free, and it gives you very accurate reconstructions compared to the original, compared to other solvers like Cirrus. Okay, so this is assuming depth is known, right? So I just want to test the scalability of this solver. Okay, so now, so then here are some reconstruction results, of building Rome in a day data set, right? So this one is the largest one, I think, was 10,000 images. Okay, so now we're going to apply it to replica data set, right? And then here, the problem is we're going to have outliers in the detections, right? So here I'm going to use detectors like, SIFT to generate correspondences, but then I'm going to robustify, XM by doing some outlier filtering. Okay, again, here are 4 different data sets with each data set was about 100 or 2,000 images. And then here there's the COMAP, which I told you is the defector approach, right? As you can see, it's very robust, but at the same time, because it's doing incremental reconstruction, it's also quite slow. And then this is GOMAP, which is a new approach last year. It was faster, but still, I think it can take hours in the large scale data sets. And here is our method, right? So it's 2,000 frames. You can reconstruct in about 10 seconds, right? So this is a large scalability improvement compared to GLOMAP and COMAP. Okay, and these are some of the reconstructions you can get from the replica data set. Okay, and then we apply it to some of the NERF neural rendering type of data sets. Here, this is using depth prediction, monocular depth prediction models. So here, there are 5 data sets also with increasing data sets. And then this is the COMAP, robust, slow, faster, but still quite slow. And this is ours, using unidepth as a prediction or as the monocular prediction depth model. As you can see, it remains quite robust in this case. And these are some of the reconstructions from NERF datasets. And also, if you do neural normal view rendering from these reconstructions, you get these very beautiful renderings from NERF. Okay, and lastly, we're going to apply this to TUM and IMC datasets. So these datasets, they are I should note that these depth prediction models, they were not trained on these datasets, right? So as you can see, if if you have a good depth prediction, seems that you can get very nice reconstructions and in a simple way as before. So depth may be a quite foundational visual capability in terms of 3D reconstruction. Okay, so that's and then here we also reconstructed a private data set with about 2,000 images, right? So here I only show you the camera views because the 3D structure is we're not supposed to show them. Okay, so an ongoing work that's we're currently working on is we're trying to generalize this method from 3D to 4D reconstruction, in the sense that if you see a video like this, right? So this is what people call casual video. Is you take your iPhone, right, and you take an image or you take a video of a certain scene. In this scene, there are objects that are static, there are objects that are dynamically moving. How can I reconstruct both the static landmarks and also the dynamically moving objects? Can I still use convex relaxation to do this? So the good news is actually you can still formulate this, this 4D reconstruction problem actually very nicely still as a QCQP, right? A quadratic constraint quadratic program. And you can, we have preliminary results showing that if you solve this problem, you get, you solve it using SDPs, the relaxation is still tight. And the craft here is, you can use these learned depths and key points to first reconstruct the static part of this scene. And then for the rest of the dynamic objects, we are going to use this technique called embedded, deformation graph from graphics. Basically, as you can see down here, is putting a deformation graph on the dynamic objects. And then I'm going to reconstruct this deformation graph using a convex relaxation. And then it's actually still a QCQP. So this is something we're trying to work on. And then the idea here is, if you use convex relaxations and these kind of fast solvers, you can basically reconstruct these any iPhone video on the internet with like maybe less than 1 second runtime, right? So that's the goal here. We can generate lots of data sets of these casual videos. Okay, so that's all about the perception part. Now I want to talk a little bit about motion planning, and let me see about time. So I probably have like maybe about 10 to 13 minutes. So I'll be little bit fast in terms of the motion planning. Okay. So the motion planning problem that we are trying to solve here is this trajectory optimization or trajectory planning problem, right? So I think for this community, this should be very well known, right? So here I have x being my state variable, u being my control variable, and fk here is my dynamics, and lk here is my stage loss and the terminal loss, right? And then I added this lambda k here just to include some of the contact implicit or contact, or problems with contact variables. So they can be discrete modes or they can be contact implicit as formulated by an NCP, for example. Right? And then these the CK here are the path constraint and contact constraints. So I'm going to assume that my problem is structured that this is a polynomial operation problem. Okay, I'll give some examples of this in the future. Oh, in the next few slides. But then for this problem, now we want to we assume it's POP and we're going to apply moment ensemble squares. But the problem here is if you apply moment ensemble squares, you immediately realize that there's a problem with this, right? So because let's say if your dynamical system has state variable 10 degrees, 10 dimension, and control variable, let's just say 5 dimension, then you have 15 dimension variables per time step, right? If my time step is 100 or 50, then you can see that you easily get a polynomial operation problem with about 1,000 variables. And I told you that if you have to apply moment ensemble squares, starting from a second order, you only generate an SDP with a million by a million matrix size, right? So in the sense that there's no solver capable of solving these type of problems. So therefore, we have to we have to ask ourselves, are there any other structures in this trajectory planning problem? And coincidentally, the Markov property, right? So one thing we know about this trajectory optimization problem is that they are decoupled in terms of time, right? So one way to see this is if I can lay out the optimization problem as a graph, right? Then the nodes here, xk minus 1, xk, and the control variables, they form a triangle, right? And then you have many of these triangles, laying out across time. And then fk here is my dynamics, which couples all these three variables, and my cost function couples these two variables. And this, path constraint couples these two. And then, but the one thing that's worth noticing is that all these coupling, they are local, right? So all these, the red blocks, they are functions that couple different variables. They are locally in this, triangle, right? And then across these triangles, there's no coupling except that you have the xk being the starting variable of the next time step, right? So basically, this allows me to basically decompose this polynomial optimization problem as a union, the variables of this problem as a union of different cliques, right? So every clique here will contain only the variables at that specific time, right? So at the case time step, I'm going to include xk minus 1, uk minus 1, lambda k minus 1, and xk. So this I'm going to call it a clique. And because this functions are locally coupled only within this clique, then I can write down this sparse polynomial optimization problem where I can write down the objective function as a sum of many different terms, where each term is only a function of the variables in the specific clique. And similarly, all the constraints are only with respect to variables in a specific clique, right? So this gives me this sparse polynomial optimization problem where now I have basically decoupled the problem into n times, where n is my time step. But there's still some coupling within the between different cliques. So this now you can invoke what people call the sparse moment SOS relaxations. So I'm going to present you the form of this problem. Nothing. So the equation in this formulation doesn't really matter. But the only thing I want you to look at is that what we call the sparse moment matrix. In the sense that before, if you had to do a moment relaxation, you'll have to create this vector of monomials in Z, right, which is all the variables. Now you only need to create the vector of monomials only in the variables in a specific clique, right? And the clique has a fixed size, right? So the clique is the size of the clique is independent of the time horizon. So therefore, you can get a very sparse SDP, and you can also guarantee that this method, this relaxation will converge to the global optimal solution of the original problem, right? Okay. So as I said, the nice thing is that if I call DC the size of the variables in every specific clique, then it's fixed. It's independent from n. So pictorially, originally you had this very large SDP with a moment matrix and some other blocks. With sparse relaxation, what you get is about many smaller, much smaller size moment matrices, but then they are coupled through this linear constraints. It turns out these kind of sparse SDPs are much easier to solve than for MOSAC and also for many other solvers than the dense SDP, right? So particularly, you can actually do your CUDA-based implementation of an ADMM solver on this type of sparse SDP, and you can scale this up. Okay, so this we just want to show you some results, right? So here is the original carpal problem. There was no contact variable in this, right? So this is a relatively small problem. But you can see that with this convex relaxations, you can generate these very nice near globally optimal trajectories swinging up the carpal. And then this is the one thing that with constraints, right? You can back up the car into between the two obstacles. And then here we use a separating hyperplane constraint to enforce collision avoidance. And then this is like a rocket landing, a simplified rocket landing problem. And then so then we started to apply this to more contact-rich problems, and then we realized that there are even more sparsity beyond what's shown in the Markov property. And then there is a principled way to exploit this sparsity by building graphs. So I'm going to skip this side. But eventually, for example, this is the graph that you would see from a typical motion planning problem, right? So this long chain here is a time, and then even within each time step, there are local couplings between these variables. So therefore, you can separate out these. You can get much smaller cliques, and then so we create this toolbox, which is basically you're going to the high level idea is you have a big positive semidefinite matrix. I'm going to decompose it into smaller ones. Okay, and then we have Python interfaces and MATLAB interfaces. Recently I've been working together with someone from Perception to reproduce many of the certifiable solvers using the Python interface, and it turns out to be very easy to use. And I hopefully we'll release this tutorial very soon. Okay, and then we apply this to contact-rich problems. I'm going to skip through these results because I want to have some time for. So this is for the last part of the talk. Okay, so this is deploying this on a real robot is relatively slow, but you can see that if you can solve every contact-rich problem to near global optimality, then you get the robustness of MPC. Right? So even with slight disturbances of the dynamics, you can push the T to the target position. Okay, so that's all I want to say about this. Now in the last 5 minutes, probably I want to spend just very quickly going through some of the challenges in using first order solvers, right? And our efforts in sort of understanding and accelerating these kind of solvers. Okay, so the motivation here for us to study first order solvers is really the perception, is really the motion planning problem, because we implemented this ADMM solver in CUDA, and we were able to see major speed ups compared to MOSAC. But the hidden message here is if you compare the accuracy of the solutions with MOSAC, then you see that these first order solvers like ADMM, they typically are only capable of solving these problems to medium accuracy, right? So here 10 to the negative 4 is sort of the KKT residual, right? And you can see that first order methods typically can only get you to the level of 10 to the negative 4. While MOSAC, they can solve the problem to 10 to the negative 8, right? So high accuracy solutions. So really the motivation here is although we can engineer these first order methods to be much more scalable than off-the-shelf interval methods, they're still far from being real time. And the other big problem is the solutions are medium accuracy, right? So although in certain cases these medium accuracy solutions are okay, but imagine if I want to use these medium if I want to use moment SOS to do let's say to certify certain bounds in quantum information theory, then we want these bounds to be extremely accurate, right? Because that's a matter of scientific accuracy, right? So the problem here is can these first order methods actually solve the problems to high accuracy? And if so, what are the bottlenecks to for them to solve these problems to high accuracy? So then we started this journey of understanding these first order methods, starting from ADMM, right? So I'm going to give you a very brief overview of this ADMM solver. So, but my view here, eventually what I want to say is that this ADMM for SDP actually eventually you can write it as a very elegant matrix dynamical system, right? Here is how I'm going to write it, right? So I have this primal dual SDP where in the primal I have A, B, and C, which is my constraints, and also my objective function, right? So if you apply the classical dual ADMM, like three-step ADMM, you have the every iteration you're going to do a linear system solve, and then you're going to do a PSD cone projection, and then you're going to do a dual update, right? So this is the classical three-step ADMM. One nice thing about this classical three-step ADMM is that you can write it as one-step ADMM, right? So here's the short proposition. I'm going to define a new matrix variable Z that's X, minus sigma times S, right? Sigma here is the dual step size. Then you can show that ADMM is basically this, matrix dynamical system, or I'm calling it FADMM, right? So it's an update on this matrix variable Z. And if you look at the update form, everything is linear, right? So A star, A echelon times A echelon inverse times A, that's the linear operator. So everything is linear in this dynamical system except the projection onto the PSD cone, right? So that's the only source of nonlinearity. Okay, and then to recover the primal dual variables, you can take the positive definite part of Z and the negative definite part of Z to get primal dual update. So this one-step ADMM is equivalent to the three-step ADMM. Okay, so this one-step ADMM, well, the nice thing is it creates much convenience for analysis. So I'm going to show you three new understandings that we currently have about this ADMM. Right? Classically, people believe that if you apply ADMM to any kind of optimization problem, convex optimization, right? So in general, except you have strong convexity or some type of local polyhedrality type of problems, then ADMM typically has sublinear convergence, right? So what we have is the first new understanding is that instead of worst case sublinear convergence, in many SDP problems you can have local linear convergence, right? So the motivation for proving this is actually if you run this ADMM on lots of SDPs, then you find that in not all of them, but in many of these SDPs, you get this very nice local linear convergence, right? So on the top plot here, I'm applying ADMM to the max cut problem, and the x-axis is the iteration number, and y-axis is the KKT residuals, right? Max KKT residue. So in the end, you see this straight line, right, which indicates linear convergence. And even when you apply, ADMM to some very hard SDPs, such as those from moment SOS relaxations, you see that the ADMM first traverses through a very slow convergence region, right? So that looks like sublinear convergence. But if you keep running ADMM, right, for long enough, there's a sudden phase transition where you're going to transit into a sharp local linear convergence region. So that gives us hope in the sense that in principle, ADMM can actually solve lots of SDPs to high accuracy, right? So that gives us hope that first order solvers are not necessarily cheap alternatives to interpol methods. They can, in principle, gives you high accuracy solutions. So then problem is, can we somehow prove this? Or what are the conditions for local linear convergence? So the first result that we have is, suppose here, and here is my little cartoonish illustration of this property, is that if you have this, let's say if you have this optimal solution set, which is a line segment, and then you have a point in this optimal solution set that satisfies strict complementarity, which is the rank of the primal dual sum up equal to 1. And then you have this, curves, which is, the dynamical system, you have your trajectories, right? So the ADMM trajectories, if the ADMM trajectories eventually converge to this strictly complementarity solution, then you can prove that eventually it'll have local linear convergence. Okay, so this is I'm not going to prove this, but this is, a major result that we believe, was not known before, right? So this gives us hope that in principle, you can solve difficult SDPs to high accuracy using ADMM. Okay, so then the next question is, yes, you have local linear convergence, but that you have to get very, very close to this specifically strict complementarity solution, which is not always the case, right? So the second type of understanding is that now we understand what's going on with lots of these slow convergence phenomena. So for example, here, these are some type of these are the SCP problems from the famous middleman benchmark. If you run ADMM for this problem, then you do not observe linear convergence, right? So then the problem here is why for these problems we do not have local linear convergence, right? And it's one step further. What is the algorithm doing in those slow convergence region? Okay, So here's one result we recently proved. I'm not, my student Shu Chen. So here is another cartoonish illustration of this phenomena. Right? Again, you have this optimal solution set, and in the middle you have the strict complementarity solution, and then everything else doesn't satisfy strict complementarity. And then for every non-strict complementarity solution, I can attach two convex cones. One is called cone A, one is called cone B. I'm not going to define them because it's very complicated to define them. So then the story here is if you have ADMM trajectories that are very close to this red non-SD solution, and if they happen to hit the regions that are inside cone A but not inside cone B, then it will move arbitrarily slowly along a straight line. Right? So the story here is, it's kind of like if we imagine these ADMM as fluids, right, or electrical fields, right? So then you have this point in this optimal solution set. What I'm telling you is that if you move very close, you're not going to converge this point. But if you're very close to this, red point, you're going to get very slow. That's the story that's here, right? So but there's a good news in the sense that it's not slow. So that there's a structure with this slow convergence in the sense that it's moving like a straight line along this line, right? So this gives us hope that if you understand this type of slow convergence, then maybe you can redesign the algorithm to bypass this slow convergence region, right? So that's the second type of understanding that we now have. So the last type of understanding is about non-local slow convergence, right? So the previous two slides, I characterized the behavior of the dynamical system near the optimal solution set. But what's going on, with this, for example, for these problems, you see that the slow convergence doesn't necessarily appear close to the optimal solution, but there are, slow convergence regions even in the transient phase of this algorithm. So what is the algorithm doing in these, non-local slow convergence regions? So that creates a major bottleneck for analysis. Because if you want to study the local behavior of the system, you can always do Taylor expansion of the system, right? So I have a nonlinear dynamical system. If I want to study the local behavior, I can do first order and second order Taylor expansion. That's very complicated, but still doable. But these non-local behaviors, there's no mathematical tool now for us to analyze this. So therefore, what we tend to think about is, we want to bring in something from physics, right? Which is actually, to analyze these algorithms as, sort of like magnetic fields, right? You have these directions of, and also the strengths of these fluids, right, or the magnetic fields converging to the optimal solution. So here I just want to give you two little examples. So the first thing is, if you apply ADMM to a linear programming, like very simple linear program, and you can plot the what we call the phase plot, right? So for people who study nonlinear dynamical systems, the first thing we study is we want to do the phase plot of this nonlinear dynamical system. Here is the phase plot of this ADMM dynamics for a linear program. And you can see that, what I'm trying to study here is if I slightly perturb the parameters of this problem, what's going to happen? So in the very left case, you have the parameter b equal to 0. You can see that you have an optimal solution set, but surprisingly, there's no slow convergence, right? The convergence is actually very fast. But then on the middle plot, you slightly perturb b to be something very, very small. Now the solution becomes unique, but then there's this emergence of this slow convergence line, what we call a phantom attractor, right? So in this line segment, you can see that all the flow gets attracted to this line segment, and then they move very, very slowly in that line segment before they exit it and they converge to the optimal solution. So this is what we call the slow convergence, phantom attractor type of slow convergence. And then what's very nice is this slow convergence line, if you stare at it, is exactly the optimal solution set of a nearby degenerate LP, right? So the line segment in the middle is exactly the line segment in the left plot, right? So this tells you that the sensitivity analysis gives you lots of things about what's going on in these slow convergence lines. So what about SDPs, right? So if you do SDPs, you get this extremely non-trivial result where now for the simple SDP I have to illustrate it in 3D. So now the optimal solution set is a disk, right? And then if you slightly perturb the solution, you see that there's again this phantom attractor where all the flow gets attracted to the disk before they exit and then converge to the unique optimal solution. So that's what we now understand about these some more intricate understanding about the nonlinear dynamical system in terms of ADMM. So I'm going to end it here, right? So I talked about the moment SOS hierarchy, and I talked about how to scale that to robotics problems by leveraging the structure. But last but definitely not the least is I think, with more understanding, with the dynamical system perspective of this first order SDP solvers, we uncover both the good news and the bad news. But then what's very important is that this new understanding now produces very natural acceleration techniques, which we are currently implementing in some of these problems, right? For example, the structure here is, if you are moving very slowly in certain slow congested region, then it turns out to be some very low dimensional manifold, right? You're moving very slowly, traverses very slowly across that manifold, right? So you can, for example, do some type of line search type of methods, right? So that's all I want to say about this this talk. And I want to thank my students who did most of the work for these problems, and also thank the funding agency for the support. That's it.
Great. Thank you so much for the nice talk, Heng. We do have time for one or two questions. So the audience, you can either just unmute yourself and go ahead. You can also ask questions in the chat. And maybe while people are preparing their questions, I can start with one little question. So I'm really curious from your experience if you think that the kind of accuracy that you get early on with ADMMs could that actually be kind of enough to maybe through some
Yeah,
rounding or something to
yeah,
actually
yeah,
get
yeah,
really good solutions? Or how often do we have to like really go to this? Because
yeah,
we
yeah, yeah.
anyway solve a relaxation, so we don't know actually how good our suboptimality gap is. So
Exactly.
yeah.
Yeah, that's a very good point, right? So as I said, for most of the problems, so for example, for the things that we did with spot, right? We solved the problem to a medium accuracy, 10 to the negative 4. And almost in all the cases, we were able to do a clever rounding and then get the feasible trajectory of the near optimal trajectory of the trajectory planning problem. And that
Hmm.
was, there was no issue with that, right? And then you get a suboptimality gap that's 10 to the negative 3. That's, that's the I think for some of the problems, it's okay for ADMN to get a low, to get slow, to have medium accuracy solution. But then it's for some other problems that that's not relevant to robotics, right? So for example, one thing that that's very another application of moment SOS hierarchy is to, for example, certify quantum disentanglement, or certify Bell inequality in quantum information theory. Then in those cases, you need to get precise values, right? Because the upper bound, the lower bound, being root square of 2 versus 1.3.9, it's actually very important for those type of things, because you want to because you want to use these moment SOS to prove certain theory, right? And also, if you think there are other type of applications of moment SOS these days about SDPs in general, which is to use SDPs to find better step sizes of first order optimization solvers, right? So there are these kind of uh, in optimization community, they are trying to use SCPs to formulate this performance estimation problem, and then they can find optimal step sizes for those problems. It also matters, right? Because finding the true optimal step sizes is probably different than finding the suboptimal step sizes, right? So I think for some other so for some problems, I think it's okay. For some other problems, perhaps we need to find high accuracy solutions. But then the final message is, if I can solve, to high accuracy using the same amount of time than before, then of course I will solve to high accuracy, right? And also, once you understand what the algorithm is doing in these slow convergence regions, then you can even spend much fewer iterations to solve to the same accuracy, right? So in general, I think our goal is perhaps not to solve every SDP to high accuracy, but rather to understand what the algorithm is doing. Previously we only have a very crude understanding about this dynamical system. Right? We only know that it's going to converge to the optimal solution set, and the convergence rate is 1/k. Right? So that's the best we have. But what we are showing here is that there's a lot of properties about the geometry of the PSD cone and also the dynamical system itself that gives you a very rich class of dynamics that's worth understanding.
Yeah, makes sense. Thank you.
Hi,
And
can you hear me?
Yes.
But yeah, so the last part was super interesting. I didn't really follow along, but like do you have an intuition like in practice what kinds of problem has these kinds of slow convergence region or probably what kinds of problem does not?
Yeah, so unfortunately, these things are very difficult to check, right? So for example, this, so this Swiss roll, this like, Maxcut G11, all these kind of problems, these are the middleman benchmark, right? So for people who don't know this, right? So this is called the middleman, if I So these are the middleman benchmark. Actually, nobody knows where the middleman benchmark comes from. But if you run these solvers on the middleman benchmark, then you always see slow convergence. So this gives a this actually tells you actually for very large family of problems there actually is slow convergence. But so
Uh,
far the conditions that we for example if you hit the point that's not, in the inside cone A but outside of cone B, these conditions are very difficult to check, right? So they're not something that you can compute, a priori before you solve the SDP, but it's more like, you have to solve the SDP and then compute these properties. It's still a posteriori check, right? But
uh,
eventually the hope is that, you have all these sorts of slow convergence regions, but the acceleration technique is going to be the same, right? Because it looks like regardless of what type of slow convergence region you are in, that region is going to be some low dimensional manifold. And then there's a way of, maybe learning the manifold and then extrapolate over that manifold. So that's so we understand now that we understand what's going on, you can try to think about a general recipe for accelerating these, right? So that's what we are currently working on. Yeah, but in terms of, in terms of what problems are so for example, for many of these trajectory optimization problems, you have slow convergence, right? So these multi-block SDPs typically have very bad slow convergence in the sense that there's some sort of ill conditioning happening in these multi-block SDPs. But for example, for these kind of perception problems, there's no slow convergence. If we actually ran ADMM for this type of problems, it's straight linear convergence. There's no slow convergence region. So I mean, my experience tells me that for first order relaxations, typically you don't have slow convergence region. For second order and even some weird SCP relaxations, you will typically have slow convergence region. But it still remains to be studied.
I see. Thank you very much.
Yeah. And I think one the other thing that's maybe this thing can help is, because SCPs are very rich, right? SCPs, they contain linear programming, they contain quadratic programming, they contain second order cone programming, right? So these results now can probably tell you a bit more about, if we use ADMM to solve QPs in trajectory planning or in some other type of context simulation, let's say. Do we have similarly, slow convergence or actually the convergence was actually fast, right? Because now that we understand more about SCPs, we can understand some subclasses like QPs, second order cone programming, things like this.
That's very interesting. Thank you.
Yeah.
Hi, Professor
Okay.
Yang. Hi.
Hey.
Hi, can you hear me? Thanks for your very interesting presentation. I'm working on the satellite navigation, and this is one type of the range-based localization and mixed integer programming. Do you have
Okay.
any comments on the SDP on the mixed integer programming problem?
Yeah. So I think you can formulate a mixed integer programming by as a polynomial optimization problem, right? So if you have integer variables, you can formulate integer variables as if they are binary, then you can formulate them as x squared equal to 1, and then you can apply moment SOS hierarchy. But my opinion is, if you have discrete variables in your polynomial optimization problem, it's better to do things like branch and cut. So what we are currently working on is we want to study a family of problems which we call mixed integer polynomial optimization problem. So in the sense that you have an optimization problem, you have two groups of variables. One group of them is binary variables or integer variables, and the other group is these kind of QCQP type of constraints, right? So you have continuous variables that are constrained by polynomial, and you have discrete variables, like integer variables. Then this gives you a mixed integer type of polynomial optimization problem. And what we are trying to do is we are going to combine methods like branch and cut, branch and bound, with lower level SDP type of relaxation. So basically, I can fix the integer variables and solve, and use moment SOS to solve the polynomial optimization problem to get a very good lower bound, and then use that to do pruning. Right? So we haven't tried this, but I think that's probably the best way to go, in the sense that if you have integer variables, then I think the branch and cut and branch and bound are a good strategy to handle integer variables than moment SOS. I think moment SOS can handle it, but my experience is when you have both integer variables and continuous variables in your optimization, and you kind of blindly apply moment SOS, my feeling is that you're going to get very large SDPs, and you're also not tight, because the integer variables tend to have different nature than the continuous variables.
Okay, thank you.
Hi, I have another quick question if time
Okay.
is.
Yeah, I would say
So-
let's say this is maybe the last question. Just
Sure.
but that's fine. Yeah.
Yeah, so in the building room experiment, there was one experiment that I think GlowMap has better solution than yours. And which is interesting because I think your method is a certified solution, but I'm not familiar with GlowMap. But does that mean that your method is certified to some specific diff, but maybe the diff
Yeah,
can
yeah.
further be optimized?
Yeah, so the problem is, when we talk about certified optimization, it's always respect to certain reward function or certain cost function, right? So here we are formulating, so the problem formulation of us is different than GlowMap, right? So GlowMap is optimizing a different objective function than us, right? So in
Yeah.
the sense that it's not immediately comparable between them, right? So I'm optimizing, so because I'm using molecular depth prediction, right? And GlowMap is not using molecular depth prediction, and maybe we are using different molecular depth predictions. So that gives us, a different objective function, right? So I can only say, okay, my solver is certified optimal for the specific objective I'm trying to optimize. But that objective to optimize may itself be wrong, right? So itself being can be improved. So I think there is work in terms of maybe differentiable optimization, right? You can learn the cost function, and then with certain you can learn the data, and then put these data into a solver, and then solve the solver, and then propagate gradients back to learn the objective function. I think maybe Frederick, she has worked on something like this before, or Connor. There are some people who have worked on differentiable SCP solvers, and then combining them with like a deep learning type of framework. I think that's very much an interesting direction. I think so far in my group we're not working on that.
Okay, got it. Thank you so much.
But the result is expected, right? So it doesn't violate the optimality, because the objective here is different.
Yeah.
All right, then I would say in the interest of time, let's finish here. And thank you again so much, Heng, for your talk. And I will just do a last quick reminder that the nominations for the paper award are open of the TC. So feel free to nominate your papers, and also please do join us for the upcoming seminars. There will be 2 in January, and you can find all of the information on the TC website. So thank you for joining today, and have a good afternoon or evening or morning, wherever you are.
Yeah. Thank you, guys. Yeah. Thank you, Frederick.
Thank you.
Bye.